Hello again everyone, welcome back to ptet.chemistry channel. So this is an actual practical paper for these 14 to 16 years old IGCSE, GCSE or O-level chemistry students. So my own students will have done this practical in one of these practical sessions, and hence I'm doing this tutorial video. So I might or might not have the chance to actually have the demonstration video appended to this tutorial video, but I mean you would probably have seen some of my other titration tutorial videos in other practical playlists on the channel. So here in this question, we have solid sodium hydroxide. So as you know, sodium hydroxide has a giant ionic structure. So it's a good to recap to think about your structure and also bonding. So anything with a giant ionic structure has a very high melting and boiling point. It's going to be a solid at room temperature and pressure. The structure has alternating cation and anions. They are repeated in this giant structure. Of course, a lot of you would have just used the aqueous sodium hydroxide. That is when you dissolve the solid ionic compound in water. Moisture, so A contains moisture, and this moisture in the air get absorbed by solid sodium hydroxide and it becomes a little bit damp. Damp means it's a little bit wet, but it's not like extremely wet. Okay, so P is a solution containing 9.82 gram per dm cube of this damp sodium hydroxide. It means that in the solution, in 1 dm cube of the solution, you have 9.82 gram of this sodium hydroxide, which is damp, so it's a bit wet to begin with. Now, you are also told that Q is sulfuric acid is 0.105 mole per dm cube. The objective of this experiment, as with any practical, any experiment, any paper 4 experimental design, experimental analysis, everything comes down to objective. What are you trying to do? What are you trying to find? Here you're trying to determine the amount of water in the sample of this sodium hydroxide, and how are you going to do it? You're going to do titration. You're going to titrate the base, the sodium hydroxide, which is a base or an alkaline, and going to titrate it with Q, which is the sulfuric acid. Sodium hydroxide and sulfuric acid give you this equation. A lot of students might have gotten this equation wrong because they don't know how to construct the balance equation, because they don't know the formula. These formulas are from year 9 chemistry as part of group 1 metal that form a +1 cation, as part of polyatomic ions that you need to remember, especially for the anion. There's also a test for sulfate as stated in the syllabus as part of qualitative analysis, chemical analysis of anion. SO4 2- is the anion present in the sulfuric acid. 2 of the H+, SO4 2-, sulfuric acid gives you sulfate salt. This is a base or an alkaline. It reacts with acid in a neutralization reaction, and you get a metal salt, which in this case is sodium sulfate, and you get water, the ionic equation of which you should be able to write. Aqueous plus H plus aqueous give you H2O liquid. Of course, here in the equation you might see it as being 2, 2, and 2, but because all of these are 2, you can divide the whole equation by 2, and it comes down to the exact same neutralization equation for every single neutralization reaction in the world. How in the world you come up with the formula of the sodium sulfate? You should probably be reminded of your year 9 chemistry, where you do the crisscross of the valency. The valency follows the charge on the ions. Of course, if you gotten the charge wrong, you're going to get the valency wrong, you're going to get the formula wrong, and you're going to get everything wrong, unfortunately. Okay, so the 2 there refers to how many of this Na plus and how many of this sulfate. You need 2 of that Na plus and 1 of that sulfate there. This is a practical setting, so it's less about theory, but I'm using it to recap a little bit of theory. It's always a good idea. Okay, as you read question, you think about your older concept there. So put Q in the burette. So Q is your sulfuric acid. So this is sulfuric acid, H2SO4. That is in the burette, and you're gonna pipette a 25.0 cm cube of P. What we have in the lab typically, at least in my school, we use this volume of pipette, but then some other schools, some other centers, you might have this particular volume, so either will be fine because your calculation is based on whatever you use. So this is quite accurate, but the problem with pipette is that they only measure a fixed volume. They're not like burette. They cannot measure like 25.1 or they cannot measure 24.9. They can only measure exactly this particular volume, at least to be quite precise actually, but they can't measure any other volume beside what they are supposed to do. they're going to titrate this P, which is your damp NaOH, with this sulfuric acid. Record your results in the table, repeating the titration as many times as necessary. Couple of things to remember about titrations. Your final reading, that means at the end, okay? So after you do a titration, after you reach endpoint, then you stop there. At the beginning, so at the start, you need to put in the value at the initial reading, not for the final reading. The volume of Q used is going to be final minus the initial reading, because at the end there, the final minus the initial reading. Going to put a tick for your best result. Remember, our maximum error margin is going to be plus minus 0.2 cm3. That is because all the burette reading, all the burette volume, including the difference for the volume of Q used, must be to 1 decimal place. This is true for the 14 to 16 years old chemistry content, whether you're doing IGCSE, GCSE, or the all-level chemistry. Okay, so I've actually done this practical because I have to compare the results with that from my students who have done it in the afternoon practical class. Whether I have whether I have the opportunity to actually put in what I've recorded is another thing for debate, because I need to try and find that video. But there are many other acid-base titration using methyl orange indicator. So here we're using methyl orange indicator. There is one on HCl and NaOH titration experiment, which I have recorded fully, and you can actually catch that tutorial if I have not had a chance to actually append my actual experimental video onto this particular tutorial. Okay, anyway, so methyl orange indicator, what do we have in the conical flask? We have the alkali or the base in the conical flask, so that means it's going to be yellow to begin with. When you have base or alkali in the conical flask, it's what you have in the conical flask, you don't add it to the burette. Okay, what's going to happen is it will go to orange at the end point. When you reach the end point, the yellow is going to turn orange, and then beyond that, if you add furthermore acid from the burette, it's going to go red or slightly pink, but usually we just call it red. This is when you have excess acid already flowing from the burette there. I'm looking down the white tile, so I'm pretty sure it hasn't reached the end point yet, so it's slowly turning there, slowly getting there. I think there is more orangey, so this is probably it just reaching the end point just now. Okay, but of course we are not trying to be exact here, we're just doing a rough titration. I'm just going to add a bit more, and still a bit orangey. It's hard to tell whether this is orange or pink. Yeah, okay, not too sure how clear the color will reflect. It's but let me just read the reading first. Just now was 3.0, now it is 26.7 minus 23.0, so that is 23.7. 23.7 should be in excess already. 23.7 is in excess. I'm just going to add a lot more and see what happens. Yeah, there's no more color change. That was definitely in excess. So 23.7 cm3 was definitely in excess. And when that is in excess, we need to be aware of what volume we need later on in order to go and be exact. 23.7 is rough tighter. It was meant to be in excess. I wasn't careful there. From my second titration onwards, I must be very careful. Alright? Some students thought, how come you can't see any color change? Because you haven't added any indicator. When you're doing acid-base titration, it's colorless. This is yellow because this is sodium hydroxide. Methyl orange is yellow when it is in base, when it is in sodium hydroxide or any kind of hydroxide. It's going to go orange when you reach the end point. It's going to go pink or kind of reddish actually when it goes to being in excess acid. Alright, so let's just get started with these titrations. I need to double check my initial volume. So there is 10 point, not too sure if you can read properly, but there is 10.0 cm3. So you will fill in your table as you go along. Yeah? My rough titration was around 23.7, so 10.0 plus 23.7 should be 33.7. But I don't want to stop there because there's in excess. I will slow down around 30 cm3. So I will let it flow until it reaches 30 cm3. Okay? So 30 cm cube is around here. So I let it go, free flow. I don't even have to swirl it or anything until it reaches 30 cm cube. That is way before it is in excess. Then I will do it drop by drop. Okay. So it's getting there. It's still there. It's going down, down, down. So we know it won't be in excess because we were being calculative. When it reached 30, that is when I will start to do it drop by drop from there and try to be exact from my second titration onwards. Right? So you might see that this thing has gone a little bit pink here. Let me just show you. So I haven't swirled it or anything. Okay, I haven't swirled it. But then when I swirl it, the pink color is gone because all you have left there is not excess acid. You still have excess of this hydroxide in there. That's why it's still yellow. Okay, so let's just focus on that. So technically speaking, I should be standing up when I'm doing this, but it's a bit tricky. All right, so I want this to be a bit there. So my eyes are no longer on the burette. I just need to get it drop by drop. This is the most difficult thing, I guess. Get it drop by drop first. Okay, so that is drop by drop. And it won't be in excess yet. Once it is drop by drop, then you swirl. Then you swirl gently. Let me just zoom in on the color change. Hopefully you should see the color change. So this is the slow bit. Okay, you need to rush the other bit, and you don't waste too much time doing 1000 titration. You do one rough, and then you try and to be exact from the second one onward. Your hand is always on the tab here because once the color changes to orange, then you stop. So at the moment it is still yellow, and when it turns orange, I think it has just turned orange actually. So this is yellow. This is before. Not too sure how clear it is, but this is yellow before any acid. There is orange at the end point. Perhaps I could just read the reading first, and if I'm not sure, I can always go and add one more drop. So my reading here is 32.8. 32.8. Alright, 32.8. Maybe I need to lift this up a little bit. 32.8 minus 10.0, that means it's 22.8. Okay, so that's my exact titer number 1. But you might think, what if I add one more drop? Before you add one more drop, you should read the reading first, okay? So notice the color. I already saw it changes because it's easier on the eye than perhaps with the video camera on the video. So I'm just going to add one more drop and see what happens. So it's pretty much still the same color, but of course if I add more and more, it's going to go beyond the yellow, orange, it's going to go to the pink. But the moment when it changes color, there's a sharp end point. You shouldn't be too far from my exact titer if you're my students, because your result will be marked based on your teacher's result. So make sure you check with the teacher, right? So that is still around 22.9, 22.8 because I already taken the difference, yeah? I'm just going to add a couple more drop and see what happened because I already took note of 22.8 as my best titer. You will see that the color has gone pink now. So just now was orange and now it has gone red. Sorry, it's a bit light, so it looks a bit pinkish, but it's actually gone a bit more red. I could add a lot more and you will see no further color change because there was already in excess acid. Level chemistry, so there's 10.0 again. And we expect to be 22.8 based on our first accurate titer. So 22.8 plus 10.0 is 32.8. So this time I don't need to slow down at 30, I can slow down at 32 because 32.8 is going to be 22.8 plus 10, which was my initial volume just now. So 32.8, so I should slow down maybe around 32. Then I'll do drop by drop just to be exact because we know we are getting closer to the end titer now. We could do this because we roughly know where we are fishing out the titer. So I'm going to wait until it goes to 32, so then I will stop. So now it is at 32. So now the burette volume is at 32. Not too sure how well you can read that because there's 33, there's 32.0. And we know there's not endpoint yet. Not the endpoint yet. You see that this goes a bit like yellowy stuff. Well, I mean orangey, kind of reddish. But now it's gone back to yellow because, there's still not the endpoint yet. Now I'm going to do drop by drop. We need to be very careful here because I'm very, very close to the endpoint, so I cannot overshoot this. Otherwise, I'll be wasting my time. I need to go slow and get it right. Go slow and get it right. Okay, hang on, not yet. Yep, so that is drop by drop. My eye is just focused on the color change. When you go from yellow all the way to orange, that is when I stop. There you go. It just turned orange. So it was just yellow a while ago and it's gone orange. And I can confirm that I have got 32.8. So that is 32.8. So I'm reading at an angle a little bit because the camera is, the video cam is kind of like slanted downwards. But if I just move this up to horizontal level, that means you should be able to read this as 32.8. Make sure that when you read burette reading, you can see it's 32 on top there and then 33 at the bottom. So that's 32. Now I already gotten my reading, so I'm just gonna put in the reading. But whatever you do, you should always do a first one, which is going to be your rough titration. You never try to be exact for your rough titration because you just need to know where you started from. Typically, teachers would tell their students to start from 0.0 or 5.0, 10.0, something convenient. I am quite an expert at titration already, so I don't really bother starting from an easy scale. It's really up to you. You have done enough alternative to practical when you see these kind of questions that that initial volume can be any sensible volume, as long as it's not starting from 30 point something or 35 point something, because by that time you might have very little volume left in the burette. Just in case your title is going to be 25 and something, you're going to run out beyond the 50.0 CNQ reading. If you have used burette before, you will know what I'm talking about. Okay, so my final reading for the rough title is 23.4. So put that into the calculator, I get 23.2. Remember, my first one is always my rough title. It's so that I roughly know the volume of my endpoint. From the second titration onwards, I need to try to do exact titrations, but I know beyond this, so maybe I'll take away 3 cm cube. So I'll slow down after I've added 20.0 cm cube, and then I'll do drop by drop after I have added 20.0 cm cube, free flow without doing drop by drop, because I'm not wasting time for the first 20.0 cm cube there. Okay, so I started from 13.1, so I top up a little bit more and I got to 13.1 cm cube. Remember, one decimal place for all the reading, including 0.0 or 13.0, and I end up with 35.9. This came down to 22.8. You should really use your calculator to do this. Okay, you cannot have an exact title with just one value, so I actually did another one. So this time I started from 0.0 and I saw happen that I got the exact title as this one. And it's very important, very important that you try to minimize your error, minimize the difference between your exact title. But you cannot just make up these things, because you are the one doing the actual practical and you risk losing everything if you're just making things up. All right, that's why you don't try and do so many. You should really try to be exact from the second one and try to get a third one that is supposed to mirror what you had done, because it is you repeating your own experiment. You're using the same solution, using the same technique. They should by right come very close to each other. But of course, sometimes we are humans and we can make a bit of error, and a little bit of error there could account for this plus minus 0.2 cm cube difference. This is the maximum allowed error margins, as you would know if you've done enough alternative to practical. But again, in reality, you try to minimize the difference there. Okay, so we need to try and put a tick on the best title. We never tick the rough title, because the rough title is a rough title for a reason. It's rough. It's going to be in excess. It is what you do so that you know roughly what volume you need to stop after you add there. So I said roughly around 20 cm cube. So 20 plus 13 is around 33 cm cube. If I start from here, I will slow down when my burette reaches 33 cm cube. Then I'll do it drop by drop, as you have seen in my other practical tutorial video with HCl and NaOH, where I demonstrated the whole procedure and explained in greater detail there. So I already ticked the best titration result. Now I'm going to calculate the average volume of Q. The Q was the one in the burette here. So read the question always. These are my two base titer. So 22.8 plus 22.8. Make sure you use bracket. I only have 2 base readings, so I divide them by 2. If I have 3 base reading, I gotta add up the 3 result and divide by 3. So this comes down to 22.8 cm cubed. Make sure that when you do averaging of burette titer, you also have it to 1 decimal place, because that is to reflect the level of accuracy from the burette volume, consistent with what you have key in the table. The volume of solution P used, that was what we pipette out. We have to fill that in because different centers will have used different kind of pipette. The one I use at my center, the students that I have use these 25.0 cm cube. If you have written down 25 cm cube, you have gotten a wrong marks there, because this is what you pipette out. Pipette is quite accurate, although it measures only a specific amount of volume there. Okay, here's where the real mole calculation stoichiometric questions start. This is the concentration of the sulfuric acid. This is the average volume of Q from the burette. So that is N equal to CV. We know that the C is the concentration of the solution in mole per dm cube. The V is the volume of the solution in dm cube. This is in cm cube. Whatever that's in cm cube, you have got to convert to dm cube by dividing by 1,000. Number one mistake, you do not have someone whispering in your ear. You got to follow the units, and it becomes part of you to actually have proper bookkeeping and think about unit. Mole per dm cube times the volume in dm cube. This is cm cube, divide by 1,000 there. Of course, if you mess up your calculation from the very beginning, so there's not much to say really. Okay, I wonder if I actually did the right stuff. I think I might have keyed in the wrong thing. You see, I have actually keyed in the wrong stuff on my calculator. So it's 2.394 times 10 to the minus 3. They did not say how many significant figure. If you look at the data here, 0.105, this 1, 2, and 3 significant figure. The volume you used, 22.8, was 1, 2, 3 significant figure. Based on the data, you should really know what is appropriate number of significant figure. That was based on the data, not random, okay? Based on the data that we have used there, as well as the volume from the burette there, 3 significant figure, 3 significant figure. I run up the answer to 3 significant figure. I look at the fourth one, it's lesser than 5, it's 2.39 times 10 to the minus 3. That's what my calculator show me. You should really know how to key this times 10 to the minus 3 there. It's basically a scientific notation. There should be an ENG button on your calculator. When you press it, it's supposed to give you 0.002394. And of course, this run up to 0.00239. What it basically means is 1, 2, and 3, that is your primary school or even lower secondary mathematics. But we avoid writing so many 0 as a scientist in physics, in chemistry, I'm not sure about biology, and the reason for it is because the more 0 you have, the more 0 you write, the more mistake you're gonna make. Alright? Using your answer from B and the equation above, calculate the mole of sodium hydroxide in the volume P used for the titration. So your titration has the mole of NaOH is to the mole of H2SO4. They want the mole. They just want the mole. So from the balance equations, I've written down the mole of NaOH, the mole of H2SO4. This is how I always set up my mole calculation. The mole of NaOH from the balance equation is 2 mole of NaOH, 1 mole of H2SO4. So 2 mole of NaOH, 2 mole of that, 1 mole of H2SO4. On the far right is the actual mole. So this is from the balance equation, and then this is the actual mole. So what is my actual mole? I want the actual mole of NaOH. I don't need the concentration or the volume. I just want the mole. If I read the question carefully, I always read before I do. I don't do and then read. I read before I do, so that I know and I can plan ahead, and I'm not going to cancel over the place because each person has only one exam paper. At the bottom there, I have the mole of sulfuric acid from the titration, 2.39 times 10 to the minus 3. That was what I given there. I would probably like to use the slightly more accurate version because I'm still using it for the next part of the calculation. So if it is your answer there, we would have rounded it up. But then for the next bit, it's always been a habit of mine to actually use the one that is more accurate significant figure, a greater degree of significant figure, so that I can continue later on. A lot of students, they like to write equal all over the place. It's always been my habit to do some very good mathematics and be mathematically correct. Therefore, I don't use equal. This means I run out of space. Technically speaking, I would like to make this a subject. I would just move this up there. So I just said that, this arrow just simply follow the step on the far right here. So the actual mole of NaOH is going to be 2/1 times 2.394 times 10 to the minus 3. I'm going to round up my final answer to 3 significant figure again to be appropriate. So I get 4.788. So there's 4.788 times 10 to the minus 3. So there's 4.79 times 10 to the minus 3 mole. This is 3 significant figure. Okay, so 4.79 times 10 to the power minus 3. I am seriously running out of space there, so perhaps I can just move that up there, maybe. Yep, that should do it. Anyway, using your answer from C, so I got the mole of sodium hydroxide and the volume there. What is going to be the concentration in P? Well, I have the mole, so the mole equal to CV. This is the mole of NaOH. I want the concentration of the NaOH, so that's N over V. So this is 4.788 times 10 to the power minus 3 mole. But at the bottom there, how much sodium hydroxide in P did I use? The volume of solution P used was 25.0 cm cubed. So convert the 25.0 into dm cubed, divide that by 1,000. Whatever you do, use bracket. Some people don't like to use bracket, and you end up making a lot of silly mistake. Okay, so you can't blame other people when you can't use your calculator properly. After this moment, I'm telling you to use your calculator very, very carefully there. 1, 2, and 3. You look at the fourth one is 5 or above, so you increase 1 to the previous value. So to 3 significant figure, it becomes 0.192 there. Using your answer from D, so that was mole per dm cube, you want the mass in gram in 1 dm cube. The mass in 1 dm cube is gram per dm cube. Mass concentration, how much mass of the solute dissolved in 1 dm cube of the solution. You're given the MR, this is in gram per mole. As you know, mole equal to mass of MR, so the mass is in gram, the MR is in gram per mole. 1 mole of something has a mass of something in gram. That is the definition of MR there. So if I divide both sides by dm cube, I'm going to follow the unit. I get mole per dm cube equal to gram per dm cube divided by gram per mole. Everything at the bottom not get affected, but gram per dm cube, mole per dm cube, because I divide both sides by dm cube there. What exactly do I want? I want the gram per dm cube, so therefore I want the mass concentration is going to be the mole per dm cube multiplied by gram per mole. Everything comes down to the one formula. Everything comes down to unit, which if you do physics, you will know exactly what I'm talking about. So 0.1952, that was mole per dm cube, and we're going to multiply that by 40 gram per mole. Typically, they don't give you the units for MR, but then this is just following through with the mathematics, following through with the bookkeeping, as well as the physics. Okay, so that will be rounded up to 3 significant figure. That will be gram per dm cube. But the question really is asking you the mass in 1 dm cube, so I just need to put down the value of the mass. There's 7.66 there. Okay, using your answer from E, calculate the mass of water present. Now you have 9.82 gram of damp sodium hydroxide. Remember this bit of the question. If you read the early bit of the question, they say 9.82 gram per dm cube. This is the mass concentration of the damp sodium hydroxide. 9.82 gram per dm cube is going to be your wet sodium hydroxide. This is going to be the only sodium hydroxide, not the water, no water, because that is just the sodium hydroxide in the solution that reacted with the sulfuric acid. The water present, the moisture that you absorb, the water that you absorb, is not going to do anything towards the acid. Only the sodium hydroxide reacts with the acid there. So therefore, what is the mass of water present? If we have 1 dm cube for both cases, it's just going to be the wet one minus the not so wet one, basically the one which is not wet, the one which only reacted with the only reacted with the sulfuric acid. So I'm gonna end up with 2.16 gram there. So that is the mass of the water present. Now the very last bit of these questions, what is the percentage by mass of water? This is by mass of water, and this is in the damp sodium hydroxide. So the damp sodium hydroxide is 9.82 gram per dm cube. Out of that dm cube, 2.16 gram is water. So 2.16 gram is water. Okay, so out of that, 2.16 gram is water from the previous bit of the question. Therefore, the percentage of water by mass is going to be the mass of the water divided by the mass of the wet sodium hydroxide, both of these in 1 dm cube there, time 100%. You're going to get 2.16 divided by 9.82 time 100. I get 21.996. So 22.0 if I convert that to 3 significant figure, 1, 2, and 3. There's more than 5, then you add 1 there, 9 plus 1 is 10, then you add 1 there, 22.0. This is percent, because the question did say percentage and we did multiply by 100%. So that's it really. That's the end of these 18 mark questions. So it's a practical question. There aren't a lot of marks in the calculations. Most of the marks are on the actual practical, which of course is a display of your practical skills. And out of the 18 marks, you probably have around 30 minutes to do these 1 question out of possibly 3 questions in the whole of your practical sessions. And therefore you should spend only about 30 to 45 minutes to finish off the practical and to get all these calculations correct. In the real thing, you don't have much opportunity to think furthermore. You just need to know things going in already. You would have been very careful about your formula, about your units and stuff, because you have enough practice by that, hopefully. Okay, so thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. I'll see you in the next tutorial video.